You are welcome to our lecture today, and we will be focusing on hypothesis testing for population parameters with small samples. And in this lecture, our key objectives are: one, to understand the foundations of hypothesis testing for small samples. If you recall, in the last lecture, the focus was on large samples. But in many practical situations, you deal with small samples. So in this lecture, we would look at the foundations of hypothesis testing for small samples. We will learn how to apply t-distribution for hypothesis testing in small samples. Recall that in large sample, we were able to invoke the central limit theorem to be able to use the Z statistics. But in small sample, we cannot invoke the central limit theorem. So the appropriate test to use is the t-distribution. We will conduct hypothesis tests for population means and proportions, as we used to do, both for when we have a single population and when we want to compare two populations, both for mean and for proportions. So we will explore practical examples to reinforce the concepts. As usual, we make ourselves to, we stimulate our discussion with pre-lecture multiple choice questions. I believe you are ready for that. So the first question is: what distribution is used for hypothesis testing with small samples? A, normal distribution; B, t-distribution; C, binomial distribution; D, uniform distribution. Even from the preamble that I've given, I think you should have idea about the correct answer. I can see Oladipupo, Njoku, Lasisi, Emmanuel, you've made your choice. Let's see others. Njoku is going for A. What distribution is used for hypothesis testing with small samples? Njoku, any other person to save? I can only see few people responding. Yeah, Ife Oluwaposimi has joined. Okay, so the correct answer is B. Those choosing A, maybe you have forgotten so quickly. In the last lecture, we talked about large sample. That's when you use the normal distribution. But when the sample size is small, the t distribution is used. So there are two conditions for using the t distribution, which we will elaborate more. One is when the sample size is less than 30 and when the population standard deviation is unknown. Remember, in the large sample, we require the sample size to be large, greater than or equal to 30, and the population standard deviation must be known. Question 2. What is the minimum requirement for the sample size to be considered small? If you also listen, then you should get this. What is the minimum requirement for the sample size to be considered small? N less than 15, N less than 30, N less or equals to 50, N less than 100. Yeah, I think, Emmanuel, I can see your response in Joku that so the correct answer is B. So small sample sizes are typically defined as those with n less than 30. So when your sample size is less than 30, then we say you are dealing with small sample. Anything 30 and above is large sample in hypothesis testing. The next question is, when testing a population mean with small samples, which statistic is used? When testing a population mean with small samples, which statistic is used? Everybody should be able to get this. Z statistic, B T statistic, C chi-square statistic, and D F statistic. So I can see Dada, Ifeoluwaposimi, Emmanuel. I think everybody seem to be going for B. That's good. So the correct answer is B. The T statistic is used when the sample size is small and the population standard deviation is unknown. The next question is, what assumption is required for using the T distribution in small sample testing? What assumption do you need for using the T distribution in small sample testing? I think by now you should also know. A, the population is normally distributed. B, the population standard deviation is known. C, the sample mean equals the population mean. D, the sample size is greater than 30. I think you should know it. Emmanuel is going for B. Dada is going for B. But you have to look at that option very clearly. I think you are confusing it. Look at it very clearly. What assumption is required for using the t-distribution in small sample testing? I've mentioned two assumptions. Yes, Dada, you seem to be Njoku, you are moving away from the correct answer, but Dada seem to be on the right path. So what is the correct answer? The correct answer is A. The t-distribution assumes that the underlying population is normally distributed, especially for small samples. There are two conditions. The second condition is that the population standard deviation is unknown, not known. For those who are choosing B, it assumes that the population standard deviation is unknown. So for you to use the T distribution, one, the underlying population is normally distributed, and two, the population standard deviation is unknown, not known. The next question is, what parameter determines the shape of the distribution? I'll be very surprised if you get this one right. But you are very intelligent, so let me see what will come out of your intelligence. What parameter determines the shape of the T distribution? Sample mean, sample size, degrees of freedom, population variance. Fairly technical for you, but let me see what your options are. Emmanuel is going for B, Dada going for B, Njoku is going for C, Emmanuel Adekola is going for A, Dada is changing his mind to C. Okay. Oh, wrong, sorry. I was reading for 4. So Timothy B, Dada C. Yes. Good enough. We got somebody who managed to get it right. So the correct answer is C. The shape of the T distribution is determined by the degrees of freedom. And the degree of freedom is calculated as the number of observations less 1. So n sample size minus 1. That gives you the degree of freedom. Now, let's go to the main issue, the focus of our discussion. So to introduce small sample hypothesis testing, Now you know that for small samples, we are no longer going to use the Z distribution, but rather we use the T distribution. And the key assumptions underlying the use of the T distribution are: one, that the population is normally distributed, and then the sample size is less than 30, and then of course the population standard deviation is unknown. These are the conditions that must be satisfied before you can use the T distribution. So why we are using it? No, because the sample size is small and the population is normally distributed, and we don't know the population standard deviation. So the reason why T distribution is preferred is because it accounts for additional variability, due to small sample sizes. Because small sample sizes can can vary, widely, but I mean compared to large, sample sizes. So that's why you need to account for the variability due to small sample sizes. So to use the test, to use the T distribution, so we will start with single population when we have just we have just single population. So maybe this is the population, and we are testing hypothesis about this population. So the usual thing is to take sample from this, and in the population the mu is the population mean, which we don't know, but the corresponding sample is the X bar. So we can test hypothesis regarding the population mean. So the usual process, as we discussed last week, you have to formulate the hypothesis. And so the hypothesis is formulated by specifying you specify the null hypothesis, and say the mean is equals to a, a specified value, which we call the mu naught, versus the alternative hypothesis, which we counter the null hypothesis and say it is not equal. And this hypothesis now is it's a two-way hypothesis. So two-way because the alternative does not specify any direction. So it's simply saying the population quantity is different. That's what this hypothesis is saying, that the population mean is different from the specified value. So after the hypothesis is formulated, the next thing is to choose your level of significance. And you recall that we can choose level of significance, which by now you should know as the type 1 error. That is the error of rejecting the null hypothesis when it is true. So we have to choose the alpha. And our alpha can be 0.01, can be 0.01, can be 0.05, can be 0.1. So, or any value in that range. Then the third step is where we are now, where you now need to give the test statistic. So the test statistic appropriate for small sample is the t-test, and this is the formula. You can quickly compare this formula now with the Z statistic. The only thing that is different with the Z statistic here is that this S, which is the sample standard deviation, has replaced the population standard deviation. So because the assumption is that the population standard deviation is unknown, then we need to estimate it using the sample standard deviation. So that has replaced sigma here. So that's the major difference between the Z and the T. So take note of that. So every other thing here is known. The X bar is obtained from the sample. The mu naught that you see here, that is, this mu naught is taken from the hypothesis. The sample standard deviation is computed from the data, and the small n is the sample size, which we should know very clearly. I believe that is very clear. So let's take an example here of testing a population mean. So we are dealing with a single population. So the scenario is that a researcher claims the average weight of a species of bird is 5 kg. So this is the population of that of the species of the bird, and in that population we don't know the population average of the species. We don't know the average population, but uh, we want to have idea. We want to estimate from the sample. So we take a sample of 10 birds from this population, or from the species of the bird, and then so 10 birds were sampled, and from that 10, the weight of each of them, the weight was measured, and then you have the average weight here. And then the standard deviation of the weight of the 10 birds was also calculated to be 0.3 kg. The alpha is, that is the level of significance chosen for this scenario is 0.05. So, but this is the claim made by the researcher. And the claim is to be tested. So the hypothesis is what you see here. The null hypothesis says that the weight is 5 kg. The alternative says the weight is different from 5 kg. So it's not specifying the direction. So it's directionless. But so the point is that the alternative is simply saying it's different. So it could be below or above. So we can now compute the t statistic. So the x bar, remember in the formula, this is x bar minus the specified value over the standard sample standard deviation divided by the square root of n. So in our calculations, we've obtained the mean to be 4.8. That's why you have it here. That's 4.8. You've obtained this is the specified value, the value specified by the researcher or speculated by the researcher is 5. So this is the mu naught. And then the sample standard deviation is 0.3. The sample size taken is 10. So when we calculate the t, this value is the value of the t statistic minus 2.15. You know, in hypothesis testing, this is the third step. The first step, specify or formulate the hypothesis. The second step, choose the level of significance. We have chosen that. The third step, calculate the t statistic. And then we are now going to the fourth, the next step, which is to determine the critical value or the decision rule. So we need to now know, how do we take a decision whether to accept the null hypothesis or to reject it. So when dealing with t statistics, first we need to calculate the degree of freedom. Is usually shortened as df. It's usually shortened as df. And is calculated as n minus 1. N minus 1. So in this case, n is 10. So that's 10 minus 1. That's how we arrive at 9 here. So we now need to look at the t table. In our previous discussion, we can use either the p-value or we use the critical value. So we are using the critical value, then you have to go to the T table. This is a T table. I think you can see it. Let me make it a bit bolder. So in this first column, this is where you have the degree of freedom in the, so you have here the degree of freedom. And on the top here, the top row, that's where you have the alpha value. But you have to be careful because you have to look at the distribution that is shown there. So the critical values is showing the upper tail probability, showing the upper tail probability. So when you look at, for instance, 0.05, then it's talking only about the upper tail, which is if the hypothesis is saying greater than the value, of the t there. But our hypothesis is two-tailed, so which means something like this. So you have to consider two-tailed. So if alpha is 0.05 and you are considering two tails, then you have to divide alpha by 2. So that means your alpha, the value you will check here will be 0.05, 0.05 divided by 2, which is going to give you 0.025. 0.025. So we are dividing alpha by 2 because we want the tail probability for the lower and the upper. This is the lower and this is the upper. So this is the lower, this is the upper. So this table is only given for the upper. So how do we now choose? We now need to look at our degree of freedom. This time, the degree of freedom is 10 minus 1, which is 9. So we have to trace that value to this place. So the value we choose now is 2.262, and that is the critical value. And that is what we call T, that is what we call the T, I don't know, the T calculated. Okay, so if you look at the slide now, so that's how we arrive at this. So which means for the lower tail is minus 2.62, for the upper it is 2.62 plus 2.62. So because this is a two-tail. So the decision rule is usually, in this case, is to compare the t that we calculated. So we compare the t that we calculated and compare it with the t that is tabulated, the T, that is the one we call the critical, the critical T. So if you go back, the T that we calculated was minus 2.11, and the critical T that we obtain from the table is 2.262. So we fail to reject if the computed T, is less than the critical T. Put differently, we reject the null hypothesis if the computed T is greater than the critical T. That's when we reject. If the computed T, the calculated T, if it is greater than the critical or the tabulated T, we reject. But in this case, the computed T, which is minus 2.11, is less than the critical T. So we fail to reject. And so, which means that claim, we cannot reject that claim. And the conclusion is that there is not enough evidence in the data to reject the claim that the mean weight is 5 kg. So this is how we take decision and conclude. So we fail to reject the null hypothesis. With that claim, we don't have sufficient evidence to reject it. If you have questions, feel free to write it in the chat menu. So let's move on to situations where we have to deal with two populations. So sometimes you have two populations, population 1, population 2, population 1, population 2. And we want to compare the mean from these two populations. We want to compare whether the average measure in population 1 is the same or different from the average measure in population 2. So you have to take a sample. So in population 1, of course, you have mean 1, and you also have, in the population 2, you have mean 2. Again, you have to take samples. So you take sample of N1 from population 1, and you take sample of N2 from population 2. So then you have to compute the sample mean from population 1 So you have X bar 1, and then you also have X bar 2. They come from the population 2. So those are the formation you need to be able to compute your statistics, but you have to specify the hypothesis. So the hypothesis is, could be specified as mu, sorry, so the hypothesis could be specified as H naught. So my barrow is misbehaving. H naught the mean of population 1 is equals to the mean of population 2 versus versus the alternative that says H2 H1 rather, that H1 that H1, that is the alternative, is such that the mean of the population 1 is not the same as the mean of the population 2. So this is alternative. So you specify you formulate the hypothesis, and then you now use the formula here. Alternatively, in specifying this, you could say H naught mu1 minus mu2 is equals to 0. It's still saying there is no difference between the average, between the mean, between the means. The alternative can also say mu1 minus mu2 is not equals to 0, and that implies that there is a difference. So look at the T statistics, the formula here. So this is coming from the, this one is coming from this mean, the sample mean from the population 1. This is the sample mean from the population 2. This is the hypothesized value for the population 1. And this is the hypothesized value for the population 2. And every other thing. But one thing here is the S square P. That is called the pooled variance. It's called the pooled variance. So the pooled variance is calculated using this expression. So it will use this formula. So to get the pooled variance, you will first of all calculate the sample variance from population 1, the sample variance from population 2, and then substitute in this expression. So that gives us the, so that will give the pooled variance. And you have to calculate the pooled variance before you calculate T statistic. So in calculating the T statistics, you have to calculate the pool variance and substitute here accordingly. So let's look at uh, a typical scenario for this, for to illustrate the difference, the testing, the hypothesis testing for the difference between two means. So in this scenario, you have two teaching methods that are implemented. You know, so so each method is treated as population. You know, so students that are taught with method A, so and students that are taught with method B. So they form the two populations. So the students that are taught with method A, 10 of them were sampled. The students that are taught with method B, 12 of them were sampled. So and the scores of the students, you know, were taken, and then the average score, which is this, the average score of the student taught with, you know, of the sample of the student taught with method A is 78. The variance is 16. For student taught with method B, the sample average is 72 and the sample variance is 20. And the chosen level of significance is 0.05. So the interest, what we want to establish is, can we say the two methods yield different mean scores? And it's like also saying whether the two methods yield the same result performance wise or not. So the hypothesis is what you see here. So the null hypothesis is saying there is no difference. The alternative is saying there is a difference. So that the average, you know, performance of the students taught with method A is not different from the average performance of the students taught with method B. And the alternative is saying there is a difference. It's not even saying whether method A is better or B is better. It's simply saying they are not the same. So this is the hypothesis. And this, you remember you have chosen your level of significance to be 0.05. So to calculate the T now, you have to calculate the P, the pooled variance. So this is N1 minus 1, that is 10 minus 1. Then 16 is the sample variance for method A. And then N2 sample size for method B minus 1. And then the sample variance for method B, and then N1 plus N2 minus 2, and that gives the sample, the pooled variance to be 18.2, and that's the 18.2 here. The 78 minus 7, that is the sample mean. This is the, for method A, this is the sample average for method B. But you know, mu1 minus mu2 is already specified to be 0, no difference. So that's why that is not there. So you have the t value to be 3.33. So before we go to the table, we need to determine the degree of freedom. The degree of freedom in this case is 20, which is n1 plus n2 minus 2 equals to 20. So with that information and with the alpha value that we have been given, we can go straight to the table now. So if we go to the table, again, because this is a two-tailed test, you have to divide that alpha by 2, and that gives you 0.025. So remember, our degree of freedom is 20. So we have to look for 20 here. We have to look for 20. So that is 2.0. Am I correct? The degree of freedom is, yes, it's 20 years. So that is how we arrive at this critical value of 2.086. This is the value here. So that's how we get the T critical. And so we will now compare this value, that's the T calculated, and the T critical. So if the T calculated is greater than the T calculated, then we reject the null hypothesis. If it is less, we do not reject the null hypothesis. But in this case, it is greater. So we reject the null hypothesis. And then once we reject the null hypothesis, we are now saying that there is a significant difference between the two, the performance of the students in the two methods. So which means in terms of the main performance, the main scores between the two methods are significantly different. So that's how we test hypothesis for a single population, and also for the mean of a single population, and also for the mean of two populations. Now we will discuss about proportions. Sometimes the issue of interest is an attribute. We are simply interested in those who possess that attribute, those who don't possess it. So we can only count the number of successes, count the number of failures. So in that case, we talk about proportion of success, the proportion of failure. So the process is the same only that the expressions for calculating the t statistic, uh, both for single population and for two populations, are slightly, the expressions are slightly different. So we start with the single population. So this is the expression. So, so if, for instance, you have a population and then you take your sample from that population, then this is the population proportion. That's the proportion of those who possess that attribute in the population. But usually we don't know, and so we have to take the sample here. When we take the sample, uh, we now look at those who possess the attribute in that sample, and that is measured in terms of p hat. This is the p naught is the hypothesized value. That is the proportion the researcher claims in the hypothesis. So every other thing there is clear. So this is the formula for testing for proportion in single population. Let's take example in this case. So in this example, we have we have it that a company is making a claim that 70% of customers prefer their product. That's their claim. Maybe two competing, uh, you know, uh, producers. So they are claiming that 70% of customers prefer their product. And to really to confirm or to verify whether this claim is true or not, so a survey of 15 customers were taken. So the customers were, you know, were to decide whether they prefer the company's product or not. And it was found that 60% of them, that's coming from the 15, 60% of them prefer the product. So can we really test whether this claim is true or not at 0.05 level of significance? In other words, if we want to take a decision that we want to be 95% confidence, that's what alpha is saying there, and be 5% doubtful. So, so we need to set up the hypothesis. So the hypothesis H naught is now specifying the claim that the population proportion is 0.7 against the alternative of that the population proportion is different from 0.7. So always remember the first thing is to formulate your hypothesis. Formulate your hypothesis. So if you have the question or if you are the researcher, then you now need to what claim are you making? What claim are you making? Or what do we know about the proportion of the population? So the T Statistic is computed using that that expression, which is the proportion estimated from the sample, which is 0.6, the claim from the population 0.7, and then P, the claim, that's the P there, and then the 1 minus P 0.3 divided by the number of observations, 15. 15 customers were chosen. So that gives us T value of minus 1.28. And then the critical value, we have to first of all know the degree of freedom, which is n minus 1, which is 14. So as usual, we have to go to the table. Since the critical value is 14, the degree of freedom rather is 14. Remember, we have to divide alpha by 2. So this is the corresponding value, 2.145. So that's how we obtain this. So both for the lower lower tail and the upper tail. So as usual, we reject the null hypothesis if the value we computed, the t value computed is greater than the t critical value. But in this case, this is the t calculated minus 1.29, which is less than the t critical. So we fail to reject. So we can conclude in this case that the null hypothesis, the claim in the null hypothesis, we don't have sufficient evidence, to reject that claim. So, which means the rate claimed by the company, the 70% claimed by the company, for now cannot be rejected because the data we have taken does not support the rejection of that claim. So finally, we look at hypothesis testing for two proportions, that is, when dealing with two populations. Just as we have to compute the pooled variance in the case of the mean, we also have to compute the pooled proportion. The pooled proportion is computed using this expression. X1, remember, is the number of successes, the number of those with the attribute in this population, the sample 1. X2 is the number of those with the required attribute in the sample 2. So we need to sum the two and divide by the sum of the sample from these two samples from the two populations. So that gives us the pooled proportion, and it is the pooled proportion that we use here. Don't forget. So, so let's look at an example in this case. So in this example, a company wants to compare the effectiveness of two marketing strategies. So strategy A and then strategy B. So the company wants to compare whether these two strategies, whether they yield the same uh, level of effectiveness or performance, not. So for strategy a sample of those that received that strategy, were taken. Sample of 20 was taken from the group that received that marketing strategy A. And then the proportion of the, the, from the population, the sample of 20 were taken, and the proportion of those that succeeded in getting the product, because that's how, maybe buy the product, is 0.6. So out of 25 of those sampled, among those who receive marketing strategy B, 0.4 of them bought the product. So, and the hypothesis, the significance is 0.05. So the idea is whether these two strategies differ in effectiveness or not. So we have to use, first we formulate the hypothesis. So the hypothesis is saying P naught, P1 minus P2. P1, we could call it PA, P minus P2, which is PB. So the null hypothesis is saying there is no difference between the effectiveness of the two marketing strategies. The alternative hypothesis HA is saying there is a difference in the effectiveness of the two marketing strategies. So we have to compute the pooled proportion. X1, which represents the number of those, because X1, that is 0.6 times 20, and then X2 is 0.4 times 25. That's how you get your X. So you have the 12 plus 10 to be 22, and then the sample size is 20 plus 25, 45. So the pooled proportion is 0.489. And that's what to substitute here to be able to get the value, the 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 proportion. Oh, this one is cut off. Sorry for that. So, and then the I think the final answer here should be 3.10. 3.10. 3.10. So you have to now look at the the T table. I mean, the T that should always be, in this case, is approximately the minimum between N1 minus 1 and N2 minus 1. N1 here is, she said, N1 is 20, so 20 minus 1, that's 19. N2 is 25, so 25 minus 1, that's 24. So the degree of freedom is approximately the minimum of the two, and the minimum is 19. So with the alpha value, we can now go to the table and look at 19. So 2.093. 2.093. So that is how the T critical value is obtained from the table. So we can now compare. Since the T that we computed is greater than the T critical, T computed 3.10 is greater than the T critical. So we reject the null hypothesis. And the conclusion now is that the effectiveness of the two marketing strategies are significantly different. So the marketing strategy A is different from the marketing strategy B. Please be careful. The conclusion does not say A is better than B, because that's not the hypothesis tested. Neither does it say B is better than A. It's simply saying no, there is a significant difference, but it's not saying A is better than B and B is better than A. So those are things. How do we now move further from there? Those are things we will learn in maybe, if not in this series, in subsequent series, as we advance in hypothesis testing or statistical inference. So this is the package for today, and we can summarize the discussion so far to say that contrary to what we have in the large sample, for small sample hypothesis, we use the T distribution. So in that case, whether we are testing for single population or we are testing for two populations, we use the T statistics once the sample size is small. Sample size is small when your sample size is less than 30. So the assumptions that allow us to use the T distribution, one, the underlying distribution is normal, only that the sample size is small. Two, the population standard deviation is unknown, so we estimate it from the sample. So these are the conditions. So we must also ensure independence. It's not only about this test alone. Independence guarantees randomness of the sample that we are drawing. When you are selecting your sample, don't be biased. You have to use uh, random sampling methods. That's when this test, whether standard, normal, set test, or test test, the, the, you must always ensure that your samples are drawn in a random manner, not in a biased manner. So we have also looked at practical applications, and there are many practical applications that we can still talk about, which may include, if you are comparing, we have looked at teaching methods, marketing strategies. In medicine, you could also look at treatment, effect. You can. So this uh, this technique can be applied in education, in agriculture, in medicine, in social sciences, economics, in engineering, many, all virtually all fits. So this is the end of our lecture. And before we uh, call it a day, so we do our usual quiz. I don't know if there are questions. Please, we have test by 4 and okay, so you can always come back to watch the video. Do we still have anybody listening? So right now, so I'll go through the remaining quiz. For a small sample size, how is the test statistic for the mean calculated? For a small sample size, how is the test statistic for the mean calculated? So look at the expressions Z. The moment you even see Z and you see sigma population standard deviation, you should rule that out. If you also come here and you see X bar mu naught, maybe this look at the others. The problem here is the S that is not squared but is inside the square root. So C may not be appropriate. For D, you have Z here and you have S here. So again, this may not be appropriate. So for small samples, the T test statistic is used, and this is the correct expression. So 2, a small sample test for 2 means assume, yes, this is very important. Assume equal population means, no. It assumes normality of the population distribution. It assumes known population variances, equal sample sizes. So you will see that the correct answer in this case is B. So small sample test for 2 means assume the population distributions are normal. Question 3, if you have the t value given, the computed t statistics, the computed t statistic given as minus 2.19, and the degree of freedom is 9. And you look at the table and the critical value is this. What will be your decision? So you have to compare the t statistic with the t critical. Will you reject H naught, fail to reject H naught, adjust the significance level, the test is inconclusive? In fact, you should first of all do away with D. In hypothesis testing, in for T and for F, the test is always conclusive. So B is the correct answer in this instance. Since T equals minus 2.5, which does not fall in the rejection region, in other words, is is not is not less than minus 2.26 and also not greater than the plus 2.26. So we fail to reject H naught. We have to, we, we fail to reject the H naught. So the, it means the evidence is not strong enough to reject H naught. Question 4. What is the formula for comparing two proportions with small sample? Yes, this one can be very trickish, but if you have followed, certainly this is not an answer. So again, if you look at this, this is also not, since you are comparing two. So again, this can also, the correct answer is A. This formula is the one used to compare proportions for small samples, which incorporate the pooled proportion. Finally, if your computed T is 3.12, degree of freedom is 14, degree of freedom is 14, the critical value that you obtain from the table is 2.145. What is the conclusion for a two-tailed test? For a two-tailed test, so remember, so A, reject H naught, fail to reject, decrease the, so increase the sample size. This is about conclusion. So these two will not even, you have to rule them out. So the correct answer is A. Since the T calculated, which is 3.12, exceeds the positive tail, which is 2.145. So we reject the null hypothesis. So this is the end of the lecture. I believe you enjoy it. I don't know if we still have anyone in the class. Thank you and see you next time. Bye.